we're going to spend some time talking about not only the security aspects of the Internet of Things that people usually think about, that people usually discuss. We're going to spend some time looking at another significant attack surface that's exposed in the majority of Internet of Things scenarios, and how fixing that in a meaningful way actually potentially involves the same technologies and techniques that we're beginning to see used in enterprise scenarios for increasing data security and access control there. So these disparate things are going to end up tying into each other, I promise. First of all, though, let's talk about what the Internet of Things actually is. The Internet of Things is largely computers. For the most part, we're not really at the point where things that aren't computers can be on the Internet. People used to be able to whistle modem connection tones, but you're not really going to successfully speak IP without using a computer. So the problems we face in the Internet of Things are pretty much the problems that we face elsewhere in computer security. We have the problem that there are computers that are out there that are not under the control of computing professionals, which have security vulnerabilities of various sorts that do not always receive software updates. The problem with Internet of Things is not that we have different problems, it's that we have the same problems multiplied by about 30 or so. There's just so many more computers than we were previously thinking about. Now, my house is something of an exception because my house already contained quite a lot of computers. And I'm also, to be fair, just stepping back a moment, a lot of the Internet of Things devices I own have been plugged in once, been reverse engineered, been dissected, had multiple security vulnerabilities identified, and then I've never plugged them in again. So I own a lot more IoT devices than I actually make use of on a regular basis. But even so, moving to this IoT model has at least doubled or tripled the number of computers inside my home. Part of that because I just really enjoy being able to shout incoherently and then my lights turn on. It's made being forward. So the Internet of Things, as I said, is mostly made up of computers. But the problem is that people don't generally buy into the Internet of Things ecosystem in order to have computers. They buy into the Internet of Things ecosystem to have other things that happen to also be computers. So the Internet of Things looks sort of like this. When people started talking about the Internet of Things, the idea was that, well, this is a great source of data. We can have internet-connected sensors that allow us to make more intelligent, informed decisions. We can use the information we have to do things like turn on heating at an appropriate time, open curtains at an appropriate time, take into account how much sunlight there is at the moment in terms of whether to close curtains or whether to open them, how to factor that into what the overall heating solution for a home would look like. By applying internet technology to sources of information, we could combine this, form a coherent policy, and make the world a better, more efficient place. So obviously, what actually happened was that we decided that basically everything, we should just stick the internet on it, and then this would be better. So we have internet-connected lights, as I alluded to earlier. It's wonderful that I recently installed some new lights, and then I discovered that with hindsight, I'd made a terrible mistake because these lights were directly opposite my TV, and my TV is reflective enough that then if I sit in front of the TV, the lights reflect off the TV, and then I can't see anything. So I solved this problem by adding more internet. And then when I turn the TV on, my Home Assistant installation notices that the TV is on and turns those specific lights off. And by some definitions, the world is now a better place because I don't need to get up and switch the lights off or take them down and install them somewhere more sensible. I do not need to live with the consequences of my failure to plan ahead. Obviously, we have connected toothbrushes because, you know, data is reasonable. The amount of time you spend brushing your teeth is clearly something you should care about. Brush your teeth. And having a toothbrush that tracks that information and then tells you whether you're brushing your teeth well is probably just another thing to feel guilty about in this world of terrible things happening the entire time. Internet-connected electrical sockets, what could possibly go wrong? Internet-connected blinds, wonderful. If I actually install some of those, then again, I could have those automatically close when my TV turns on, depending on how sunny it is or not. And that would be another way for me to be lazy. TVs, obviously, internet-connected, both useful in terms of me being able to do stuff in response to the TV being turned on, and also me being able to now track how much time I spend watching TV. Also used because there's now much more entertainment on the internet than there is on any other data source, so having an internet-connected TV makes it easier to get that. Thermostats, yeah, thermostats, things that actually make some amount of surprising sense. A reasonably intelligent thermostat will do a much better job of knowing how your home behaves, how much time your heating should be switched on for in advance of a specific point in time to hit that temperature point without overshooting, without spending extra unnecessary amounts of energy. Thermostats, actually a nice Internet of Things story. They are a thing that does actually potentially make the world a better place. Medical devices of various sorts. One of the amazing ones here is so CPAP machines for people with sleep apnea, devices that basically force air into you while you're asleep to avoid you suffocating while you're asleep. That insurance companies will provide as a discount, and then someone as an insurance company was, well, how do we know that people are actually making use of these expensive devices that we, the insurance company, have paid for with the insurance premiums that they paid us? And decided that the best thing to do would be to track how much time people spend using these, and then upload that data and make it available to your insurance company so they can make sure that you actually use this device in the way it's meant to be used. And if you don't, then they threaten to make your insurance more expensive. Door locks. You can open your door over the internet. You can also, to be fair, if you're out of home, look at your phone and determine whether or not you did actually lock your door, which is then something which alleviates anxiety and potentially makes the world better. Scooters, those rental electric scooters, I'll be coming back to those. Cars. A lot of cars you buy these days have built-in internet connectivity for a mixture of maintenance purposes, for various other sorts of data collection and tracking, and nominally for things like, oh, automatically make an appointment when I need an oil change, that sort of stuff. Also be coming back to cars a little. Beer makers. I bought an internet-connected beer maker. I had reasons. And this one's especially wonderful because now, when I turn it on, it takes 5 minutes to boot, doing nothing before it times out and finally succeeds because the company went bust and the servers went down. So there's a whole lot of things here, and they have a couple of things in common. So the first is that they're all computers, and the second is that they're all online. Now, despite us talking about this in terms of IoT, the Internet of Things, in many cases, these are not actually Internet connected. They're more the intranet of things. There's plenty of IP-connected devices that do not connect to the Internet as a whole, unless you're in my home where, so my ISP was WebPass. The entire building of about 200 units had one IPv4 address, and then there was carrier-grade NAT for the entire building. So there was just one DHCP server. So rather than put an additional router in myself, I just plugged a switch into the socket, and then everything DHCP'd, and then I was just NATed at the building level. And that was convenient because if I went down to the cafe in the building, I could connect back to my home devices. And then one day, I discovered that I could only speak to about 50% of the devices in my home. And I spent some time trying to debug this, and I noticed that the devices that had recently renewed their DHCP lease were now on different IP addresses. And it turns out that WebPass had been acquired by Google, and Google had given them a bunch of actual IPv4 addresses. The reason they were doing one per building is that they'd run out. And my devices that didn't have a router between them and the carrier-grade NAT router were now being given world routable IPv4 addresses, and suddenly my light switches were all online on the public internet. So in that case, devices that had not previously been on the internet were suddenly on the internet, and that was an issue. But yeah, I fixed that, mostly. So they are all online, and this does mean that they fall into a set of circumstances where they have the same set of problems that we face with other online computers. That is, people who are on the local network can attack them. Ones which have internet connectivity are generally connected to some sort of cloud service, and so we can potentially also attack these devices remotely via this cloud surface. And depressingly, not all attacks require you to be on the internet or the local network at all. There are certain attacks you can do that bypass any of the security mitigations that might be associated with the first two of these, and we'll cover those a little bit later. So obviously, we're putting devices online. We understand that there are various ways that they could be attacked, and we know that computers as a whole are even securely designed systems are not generally 100% secure. So we're putting these things here. We need to start thinking about how secure are they? And the answer to that is that it varies massively. There are IoT devices that are genuinely well implemented, that are as secure as is really viable given current engineering practices and software design expertise. We are in a world where we still basically, as a society, have no idea how to make computer good. So software is then even worse than the hardware. And IoT pretty much covers the entire range. There are some IoT devices that are extremely well implemented. Weirdly, of all the IoT devices I've looked at, the one that I actually ended up with the most trust in afterwards was the internet-connected speaking Barbie, where they had clearly been very, very aware that hackers made Barbie tell my daughter or son to murder their parents would be something of a PR disaster. And as a result, had done a massive amount of work to ensure that this didn't happen, that internet-connected Barbie was not going to be a disaster along these lines. And they actually ended up delaying the release by several months to satisfy all their concerns. So yeah, it's possible to produce secure internet-connected devices. Most people don't bother, which is obviously disheartening. On the other hand, it's given me a near inexhaustible supply of conference presentation materials, so who can say whether this is good or bad? So we're going to break this down. And what does a local attack look like? So this is a scenario where I am on the same network as your IoT device. And the general failures that end up appearing here start with, what authentication is there on the device? And honestly, for a lot of local network purposes, the answer is there is no authentication. The threat model is if you're on the local network, you're already trusted. And so this is sort of network-based security. And that sounds like a terrible idea. But then think about it. How many of you work for companies where in order to access internal resources, you need to VPN into your company? Right, so a bunch of you have to do that. How many of you work for companies where if you are on your company's network, you do not need to VPN in order to gain access to those resources? Right. So that's a network trust-based model. The idea that you have managed to get onto this internal network demonstrates that you're trustworthy, and security barriers that would otherwise be there are not there. You don't need additional authentication to reach these. We'll get back to that later. There are also devices that have authentication, but are doing stuff like just sending that over the wire in clear text, or where there's enough information leakage for you to be able to reconstruct the authentication, or where the authentication is not a password, it's some sort of fixed or per device authentication token that can be derived from other information about the device. There are cases where there's something running on the device which has vulnerabilities. I looked at one Internet Smart Socket that was running a debug daemon locally, even on production builds. And the debug daemon, you could send it various commands, and then it would do stuff and tell you something about the state of the system in response. One of the commands was tell me whether this process is running. The way that was implemented was you sent a packet with the name of the process in, and then it ran system ps pipe grep, whatever process name you passed in, and then based on that it said yes or no. Problem is, if you asked it to check for the state of a process which had a semicolon in it, it would then split that into another command. So you could, and for some reason it shipped with netcat, so you could then just do semicolon bash pipe netcat blah and just get it to launch a network shell. There are others which are less bad in this respect, but then you know, if you're doing IoT security research, then the top trick I'm going to give you is just start by extracting the firmware from the device. It's probably running Linux. If it is, just look for which binaries on there ever call the system library call, because basically every single one of them does that is vulnerable. People are so bad at software. But then even outside the trivial ones, you're still going to end up with these standard sorts of buffer overflows, double freeze, use after free. And this is relevant in most cases because a lot of these embedded devices are not built with modern security standards. They don't have address space layout randomization or anything like that. In some cases, you have devices running weird custom operating systems that have terrible IP stacks, and it's just a matter of sending malformed network traffic, and then the kernel will do whatever you want. So how about when you're not on the local network, when you're attacking the machine over the cloud API that's provided instead? Sometimes, again, we find that there are API endpoints that do not full authentication and which you can hit and gain stuff. And then there are API endpoints that do stuff like allow you to perform SQL injection attacks, where they haven't actually performed any escapes. You can send something that does a database query, you've put in some meta characters, and then you can do your own database query instead. Or cases where you can trigger arbitrary code execution. And then there's the standard problem you have where you're running something on a computer, which is that there are other things also running on the computer, and if those other things on the computer are not also secure, it doesn't matter how secure your thing is, because an attacker can attack the insecure things and then attack your thing locally. So, yeah. Different but related set of security concerns when we're attacking the cloud side of things. And then there are cases where you don't need a network to perform an attack. So sometimes this is because the device has other exposed attack surface. So the Bird e-scooters, how many of you have seen those? They're rental e-scooters from a company called Bird. So just want to say first, they fixed this, so this is no longer a concern. But so these scooters have an internet connection so that they can report. So you walk over, you scan the QR code on one, you say, I want to rent this. Your phone sends a command to the cloud API. The cloud backend sends a command to the scooter, telling the scooter to unlock. So the majority of the communication is over the internet. But they also have a Bluetooth stack running on them that would accept some sorts of commands. And those were so that people could say, recover unlock and recover devices that had fallen off the network for any reason. And the authentication for this was you generated an AES key with two static things, one additional piece of information that the scooter would just give you, and then the fourth quadrant of this key was made up of the scooter serial number passed to the A2I function, which takes a string representation of a number and gives you the integer representation. Unfortunately, these scooter serial numbers all started with a letter, and therefore A2I always returns 0. Yeah, so that was a case where you could just walk up to a scooter, type some stuff, hit enter, and then the scooter would go beep, and you could write off on the scooter. And obviously, I didn't do that. But that was a case where, so to be fair, the cloud service would then, after a couple of minutes, notice that a scooter was unlocked when it should be locked and would lock the scooter again. Thankfully, it would not lock it while it was moving. That would have been unfortunate. So this is a case where even if your internet-connected components are secure, if you're exposing other remote attack surface, you still have potential security vulnerabilities. And then there's interference with the network itself. So those Ring doorbells, the ones that you put on your door, and then you find people stealing your packages, and then the police demand all the footage because maybe someone did something nearby. I find these things terrifying. When you install the Ring app, it encourages you to enroll in the Ring neighborhood community, and then you suddenly get push notifications anytime someone within a couple of miles of you thinks they've seen a criminal, which results in you spending your entire life being convinced that you're surrounded by crime and you should buy more security products, which is an amazing marketing strategy. I'm in awe of this weaponized evil. So I'm not a huge fan of these things, and I poked around a bit and discovered that, well, they're on the internet, but they can only they don't store any video locally. They can only stream video. So if you disrupt their network connection by, say, one of the wonderful things about the 802.11 network protocol is that in current versions, up to and including anything with WPA2 as the authentication encryption layer, management frames are not encrypted. If you can see a wireless network, even if you can't get onto it, you can inject management frames onto that network. And one of the management frames you can send is a disassociation frame that tells the access point that this device no longer wants to be on the network, and you can send onto the device telling it that the access point no longer wants you to be on this network, and then the device falls off the network and stops streaming video, which is great. So there's a nice open source project. You can get the designs for a PCB to build a disassociated device, and then you can hack that firmware lightly so that it automatically identifies when one of these doorbells starts attempting to join a network, and then immediately starts spamming it with the authentication frames, and then you can just walk past these things. They don't record you. This might be illegal. You should ask a lawyer. Certainly not encouraging you to do this. So you're still, even if your software stack is secure, for your product to work, you're still relying on infrastructure that's not directly under your control and the security of that infrastructure. So what's the damage here? In some cases, this is just annoyance. If somebody's able to prevent you from turning your lights on, that's largely a thing that's annoying. Worst case scenario, you turn them off at the physical switch, turn them on, and then they turn on again, in general. Potentially physical damage. So if you have an internet-connected electrical socket and you have, say, an air conditioner or heater or something plugged into that, then rapidly cycling that on and off has potential for damaging the device and potentially also causing damage to other bits of home infrastructure, especially if it's a poorly designed thing that then catches fire. But also privacy violations. If I'm able to connect to a cloud service or a device, and I'm able to see what you're doing, I suddenly have insight into your activities. If I'm able to tell when your lights are turning on or off, I know things about your behavior that you would potentially not want me to know. If I'm able to, say, track a scooter, and I know where you are starting from, if I think it's you on that scooter, I can then see where you go, if I'm able to query the location of that scooter repeatedly. So there's various ways that even if we don't think that these are fundamental security problems, if they're not cases where someone's going to use this to break into your network, where someone's not going to use this to burn your house down or crash your car, there's still potentially real-world consequences to security issues here. We often sort of ignore the impact of privacy leakage. So that all sounds horrifying. We've already determined that there's a lot of ways to attack these things. And this is the sort of space that people tend to look at when they're doing security research of IoT devices. They're looking at the interfaces that the user communicates with, that the app communicates with. But the device has to talk to something as well. If there's a cloud service, how does the cloud service know to pass your queries from the app to the device? There needs to be some way for the device to connect to the cloud's backend. And that's an entire additional attack surface that is largely ignored. What does that interface look like, and what does that network traffic look like? So yeah, we have these devices connecting to this API. We have these devices reporting state about themselves, and we have these devices receiving commands. It turns out that for some of these devices, even if you have a strongly authenticated encrypted communications channel between the user and the cloud service, the communication between the cloud service and the device is not necessarily encrypted at all. The protocols do not always look anything like each other. And this is a target-rich environment, it transpires. But the first thing we need to think about is, OK, a device is going to contact this cloud service. It's going to need to authenticate to that service somehow. And how do you authenticate a device? The device is generally not something where the device is normally not connecting and giving a unique username and password, because that isn't really how things work. What turns out to happen a lot of the time is that the device authenticates using its serial number. It just connects and says, hi, I am a device of this type with this serial number. And then the cloud service is cool. And then the cloud service associates that serial number with a specific user. The user connects to the cloud service. The user says, hi, I would like to control this device. The cloud service looks at the serial number you want to talk to, sees whether that's a serial number that is registered to your account, checks whether a device with that serial number is currently connected, and then sends the commands to that device. Some devices don't use the serial number. Some devices use the device MAC address. In some cases, the MAC address and the serial number are actually the same thing. And then there's a small number of cases where there's something actually cryptographic, where the device connects and asks the server to give it some sort of challenge. The server encrypts something, passes it back, and then the device decrypts that and passes back the token to prove that it has control of this cryptographic identity that the server associates with it. So there's, get into details of that in a moment. So one of these is somewhat more secure than the others. It turns out that if you know one device's serial number, you can infer what another device's serial number might be. It's probably, if you add one to the serial number, that's probably still a valid serial number. That's actually what the word serial means. MAC addresses, you can look at the prefix many hardware vendors will use their own MAC address range. So if they do that, then you can infer additional good MAC addresses by just, again, incrementing the MAC address you're looking at. That's probably then going to be another of the same sort of devices. So the cryptographic identity is a much stronger one. The problem here is that if the cryptographic identity is just stored on the device, then anyone who has access to the device can probably extract that cryptographic identity. So you don't want to just have a identical cryptographic identity on every device. You want every device to have its own unique cryptographic identity, so when you talk to it based on the identity it provides, you know which specific device it is. The cloud API service, the backend, is it's largely not very well protected. If you just intercept traffic between the backend service, you can discover that, like I mentioned, a lot of the time this protocol is actually clear text. The idea being that no sensitive material is going over it. And the amount of authentication is very low. In some cases, it is literally, device shows up, says, hi, I have this serial number, and then you have access to the entire backend API. So that's not great. But OK, let's step back a minute. Say you have a device that you need to authenticate to. There's two ways you can do this. The first, well, so you have some sort of password. The first is that the device is not involved in the authentication process at all. You connect to the cloud service authenticates you, and then passes your commands to the device. But say you want to have authentication on the local network as well. You don't want to trust the local network. Then the device needs to know its own password. So when you communicate with the device on your local network, you're still able to authenticate. And you ideally don't want the cloud password and the device password to get out of sync, because that's just confusing for the user. So the easiest way of doing this is to connect to the cloud service, provide your credentials to the cloud service, and then the cloud service reaches out to the device and authenticates against that. And this is a problem because OK, imagine a hypothetical scenario where you're a company that has implemented something like this. The password is stored on the device, and so you want to provide a challenge to the device, and so the device can then say, yes, this is the correct password. One way you could do that would be to say, take the user's password, MD5 it, send the MD5 unsalted hash to the device, and then have the device say yes or no. So if you did that, anybody who could see the network traffic would be able to then extract this unsalted MD5 password and then just brute force that and get the password. But that would involve them having to be on the network somewhere, able to observe this traffic. But instead, what if you connected to the cloud service and said, hi, I am the device with this serial number, and then you sat there and waited, and then the cloud service sent you the password hash instead of the actual device, because the cloud service has no way of telling the difference between a legitimate device and someone pretending to be the device. So you could potentially, if you know the entire serial number range, just make many thousands of connections to the server pretending to be every device, and then wait for password hashes to be delivered to you. Obviously, again, I have not done this. So the damage here is that we can potentially lose some amount of personal information. If someone connects to the API backend server pretending to be your lighting control device, they're going to know when you attempt to turn your lights on. There's password loss, as I just described. There's also a case that isn't really a problem from a security perspective, but has an interesting economic impact. Say you're a company that wants to make IoT devices. First, don't. But say you've decided to anyway, regardless of my extremely good advice. Now, to do this, you're going to need some cloud infrastructure. So the normal way you would do this, you'd employ some developers, you'd give Amazon a bag of money, or GCP, or cloud service of your choice. And then your users, you'd write an app, your users would install the app, and then, you have all this infrastructure. Alternatively, you could, say, pay a third party, and there's a few companies that provide IoT platforms where you integrate with that and then put your own branding on stuff, but they run it all. And then there's the third option, which is that because there's no authentication, you just make devices that pretend to be another manufacturer's device, and you use that manufacturer's backend instead. So having completely unauthenticated access to these things is actually something that has economic impact. And I've seen cases of Chinese companies largely selling cheap IoT devices that are using someone else's infrastructure and app without any business relationship with them. I think that's beautiful. But there's also other meaningful privacy implications. So there was a case recently in the UK where someone was accused of murdering someone. Someone was shot with a crossbow, and they immediately suspected his neighbor, who was a crossbow enthusiast. So first off, okay. But they were not able to prove that the only person within 15 miles with a crossbow was the person who shot him with a crossbow. So they looked for other evidence. And the other evidence they found was that his car reported being driven to his neighbor's home, sitting there for a while, then the trunk being opened, a couple of minutes later, the trunk being closed, and then the car being driven to a beach, the trunk being opened, and a couple of minutes later, the trunk being closed, and then that's the beach where the body was found. So this seems like a reasonably straightforward, well, okay, open and shut case. How did the car authenticate to the backend service when reporting its location? Can you frame your neighbor for a crime by faking the identity of their car and then making it look like their car drove somewhere that their car did not in fact drive? How good is the implementation here? I legitimately have not done this. In terms of I've never murdered anyone with a crossbow, and I've not actually attempted to attack any car manufacturer's backend services. And then finally, one sort of interesting case. So some companies with an interest in producing self-driving cars have cars that are currently not self-driving, but which record a whole bunch of data that they then upload to the cloud that can then be used for training purposes. How do you know that that training data is coming from a car that hasn't been compromised and is not providing training data that's been tampered with in an attempt to generate a poisoned machine learning model that then drives a specific person off a specific cliff? And if you want to kill someone, there's much easier ways of doing it. So this isn't going to happen. But how are you actually verifying this sort of thing? So the thing that all of these have in common is that we're failing to solidly identify the identity of the device. We are trusting the device to self-report its identity in a way that someone else can fake. And that's a problem. You really want to know, for a number of reasons, that the device you're talking to is actually the device you think it is. You want some way to prove that. And the current state of this in IoT is that this is an almost completely unsolved problem. There are some devices that do have their own unique cryptographic identity, and in those cases, so some of these, it's baked into the hardware, but in general, that's something that is recreated on a factory reset. And that's fine in terms of ensuring that you can't spoof a user's device, but that's still a case where you can generate your own key pair and pretend to be a legitimate device. So that's a case where you can't attack the user, but you can still engage in the economic damage case, where you piggyback off someone else's infrastructure. So by and large, this is not a problem the IoT solution, the IoT industry has a solution for. So how do we solve this in the non-IoT space? How do we solve this on the computers that are actually good and secure? And this is my job. Something of a segue here. So the best way of doing this is to have a cryptographic device identity that is fundamentally bound to the device. There's a couple of ways we can give a device cryptographic identity. The first is we can generate a key pair and put that on the device. And the second is that the cryptographic identity can actually be intrinsic to the device. Wow, I feel inadequate. Yeah, OK. Provision secrets aren't ideal. If there's no intrinsic binding between the secrets, between the cryptographic identity and the device identity, then someone is potentially able to spoof that at some point. If they're able to fake the identity of the device while you're provisioning the secret, then you end up with an incorrect idea of which device you're talking to. So you are given a laptop. Someone says, this laptop has this serial number. You don't check that. You provision it. And it turns out that your provisioning of that secret has actually gone to a device with a different serial number. Then your device binding is less strong. The other is that, depending on how you do this, if the secrets are, say, just sitting on local storage, if someone's able to extract those secrets, they can duplicate the device identity. So that's suboptimal. If you've got a PC, it has something called a Trusted Platform Module on it, or a TPM. Now, the TPM is something that does some amount of cryptographic work. It stores secrets. It's not a crypto accelerator. It's slow. It's resource constrained. It doesn't do that much. But every TPM has an intrinsic identity, something called the endorsement key. And this is a key pair that is generated on the TPM during TPM manufacturing. The TPM manufacturer then provides a certificate, like an SSL certificate, that chains that key back to the TPM manufacturer and includes stuff like the TPM serial number. So that's where we're able to say, OK, based on this cryptographic identity, we know what this TPM is. And because TPMs are soldered to the motherboard, that pretty much ties the TPM identity to the device. Now, that's not perfect, because we're still then sort of using the TPM identity as a proxy for the device identity. But the industry is moving towards providing something called platform certificates, where as well as the certificates that the TPM manufacturer produces, you get an additional certificate that your hardware manufacturer produces that ties the TPM identity to the device identity. And so that way, you can look at the device identity and you can assert, OK, if I'm talking to a machine that has this cryptographic identity, I am talking to a machine that has this serial number. So going back to the earlier question about network trust, where we basically say, OK, if you're on the VPN or if you're on the internal network, you're trusted and you can access internal resources. By having a strong idea of device identity, instead of trusting something just because it's on the network, you can instead decide whether or not to trust something based on its identity. So this way, you can say, even if you're on my local network, I will not give you access to this resource unless you're a device I recognize, unless you're a device I expected to be here. And you can also potentially tie that into other stuff. TPM-based remote attestation gives you not only the device identity, it gives you information about the device state. You can find out what a device, which firmware version a device had when it booted. You can tell which operating system it booted. And you can say, OK, this machine has not had all the appropriate security patches, therefore I'm not giving it access to sensitive material. I will potentially instead just give it access to the server that has the firmware updates or the patch system. So you can then have very fine-grained grant access to different subsets of devices. You can tie that to user identity, and everything is much better. So this, there's a design concept called Beyond Corp, Beyond CORP, which there's a white paper published on that. Various companies have implementations for this. Device identity is a key part of Beyond Corp, and using TPM identity as the device identity is something that my team is currently working on in order to strengthen this even further. The PC industry is not really there yet. There's not many good implementations of remote attestation infrastructure or device identity validation based on TPMs. Platform certificates are not being issued. It also turns out that in a lot of cases, the data reported by the TPM is incomplete and not verifiable, even in cases where stuff comes from reputable manufacturers. So just going to suggest that the PC industry is by and large ahead of IoT. So in a case where the PC industry is not really there yet, yeah. The IoT industry is, for the most part, a really long way away from having a strong device identity model and doesn't, for the most part, yet have any of the infrastructure in place to handle any of these problems well. Now, obviously, this is a case where I come along, I start talking about TPMs, I start talking about verifying device identity and potentially verifying device state before you have access to something, and then that turns into you're trying to tell me that my life will be better if I have devices that I can no longer hack, devices I can no longer run my own software on, devices I cannot improve. And my response to that is, well, yeah, that's a great point to bring up. And my argument is that we can decouple these. For IoT stuff, there's not necessarily any reason to tie device state into part of this. What you really care about is the device identity, but you could also proxy the device state to the user. The user is then in a position to know whether their device is running the software the manufacturer provided or whether it's running modified software. And then the user's in a position to be able to make a judgment on, well, I didn't modify this software, so this seems bad, versus, well, yes, I modified the software, this is fine. We can make use of all of this in a way that provides the security benefits without having any negative impact on user freedom. And I think the important thing to do is to firstly be aware that this is a potential threat, that as the IoT industry is pushed in the direction of having more and better security, the response is going to be, we should lock these devices down more strongly and make it harder for users to change anything. We need to push back on that, but we need to do so in a way that recognizes that the security concerns being raised are legitimate, and there are real-world consequences for not improving the security of things. We can't just say, freedom is more important than security, therefore don't do the security work. We need to be able to say, we have a story for how you get both security and respect the user's freedoms. Is this necessary? We'll see. I gave you a whole bunch of cases where this sort of issue could be used to cause harm. We haven't really seen any real-world cases for that. And whether this is because people are just not really looking at it yet, or whether people are, by and large, not into making other people's lives miserable or framing their neighbors for murder, we don't know yet. There's certainly the argument that it's only going to take one high-visibility case of this for the public to be concerned and for the public to have a negative reaction to anybody who doesn't do the security work. So there is something of an incentive for the industry to make things better, even if there has been no demonstrated strong threats yet. Finally, the code my team has been working on to implement strong device identity and attestation on PC devices with TPMs, written in Go, mostly complete. It's on GitHub, it's fully open source. We do all our development in GitHub first and then bring that back into our internal code. So everything that's not tied directly to our internal infrastructure is there. So if you make use of that, you're not missing out on, we don't have anything secret and magical in comparison. So a few minutes left for questions. Anyone? No? Is there a microphone? Oh, I have the microphone. Just. Are there any government regulatory requirements around this? Not that I'm aware of in terms of requirements. NIST in the US does have some guidance for how to do this well. I don't know of any general purpose. I don't know of any sort of consumer level products that assert any sort of conformance to any NIST standards here. It's been hard enough getting PCs to start implementing various NIST requirements. So I don't think there's any regulatory requirement anywhere yet. So the question was, how do we avoid implementing security in such a way that when a vendor goes out of business, the devices become unusable? So in this case, with what I'm suggesting, if the devices are not locked down, if the devices are in a state where you can replace the software on them, then having a strong device identity and having strong security built around that does not stop you from switching that software with something that contacts a different backend, and then making it possible for someone else to build an alternative implementation of infrastructure. I think it's going to be interesting seeing whether that does start happening. We're seeing companies start threatening to disable old devices because they're sufficiently resource constrained that it's not straightforward. Well, the nominal reason is usually they're sufficiently resource constrained. It's difficult to keep up with other protocol improvements. Or alternatively, it's to encourage people to buy new versions of something they already have. It's going to be interesting seeing whether there is any movement to build alternative infrastructure and then port devices over to that, and whether we can actually, at a social level, make it encourage companies, or if necessary, force companies to make this possible. I think there's a strong argument around devices that become paperweights that we have to throw out because someone shut down infrastructure. We should be viscerally horrified about that. We should not be okay increasing the amount of waste. And I'm okay with companies saying, we are unwilling to support this anymore, but we will make it as straightforward as possible for someone else to take that job over. And users will have to explicitly shift over to that, and then it's not our problem anymore. I don't think it should be an obligation on a company's part to say, we sold this, therefore we will support it forever, as long as it is viable for someone else to do that work. So that's the future I'd like to see. I don't see any incompatibility between that and security. Any more questions? Yeah. Is there an index of what's good and what's bad? Not really. So one of the problems is that, doing a security audit of something does not guarantee that there are no security issues. I can spend a couple of hours looking at a device, and I can say, this feels good. I haven't found anything obviously wrong. And I can spend a couple of hours looking at something and say, OK, I didn't find anything, but everything about this makes me feel icky. Turns out that if you write a sort of index of things with this product makes me feel icky, then companies get unhappy about that because you didn't prove there was any security issues, so why are you libeling them? So the answer is not really, and it's very difficult to say that we could do that well. One of the problems with saying this thing appears to be secure is that if a security vulnerability is then found, that seems to discredit you. As an industry, it is arguably inappropriate for us to say this is secure. What we can say is that as an individual, I would place my trust in this thing. In terms of, obviously, I work for Google. I'm not going to talk about Google products because that's just inappropriate. Of the devices I've looked at, honestly, the Philips Hue stuff is implemented the way I would hope it was implemented. The local authentication story is a bit plain text, is a bit weak, but you're on the local network. What are you going to do? The remote authentication story is cryptographically backed. You cannot impersonate someone else's Hue device. And even better, when you factory reset a Hue device, it generates a completely new cryptographic identity. So even if someone has gained access to your device and copied that key identity, someone resets it, you can no longer impersonate it. It's effectively a new hub for that purpose. So there are design decisions like that. I can look at that and I can say, OK, this is how these things should be done. So if they've done these things right, they've probably done other things right. And so that leaves me feeling comfortable. I would tend to trust them. Otherwise, I don't believe there's any widespread analysis of this. Any more questions? Yeah, definitely. So things that include military-grade encryption, the line scooters, the green ones, they have a Bluetooth identifier that is a hash string that turns out to be the scooter's IMEI triple-desed with a static key and then truncated in half. This is largely pointless, but also, yeah, that's military-grade. Just because something can be military grade doesn't mean that applying it to every situation makes anything better. Time for maybe one more question? Anyone? Back there.
Are you familiar with Shodan?
Familiar with Shodan? Yes. Shodan.io is a website that basically scans the entire internet and then collects metadata about what it finds. So you find a vulnerability in something, you can then ask Shodan how many cases of this are exposed to the public internet. One example of that is that the Intel reference UPnP server that was used in a lot of both IoT and Wi-Fi routers had an interesting behavior where you would send it a GET request, and it would send you a mixture of stuff that's constructed by code or static material off disk. By default, if you sent it a PUT request, it would save whatever you sent it onto the local file system. Now, usually it was running chrooted, so you were not able to just overwrite the password file. But there's something like 4 million devices running this on the public internet. So it turns out it's a really useful distributed file system. Hypothetically. So yeah, Shodan was incredibly useful in identifying the scale of that problem. So I think I'm out of time. Thank you all for coming along.